So let's continue on with Lecture 5B on thermodynamics. And now we're going to focus more on this idea of heat and work, Q and W. How are they related, and is there anything else that we can learn from this idea of heat and work? And so one of the things that we do know about heat is that it moves from an area of high heat to one of low heat. This probably shouldn't surprise you. You know that if you touch something warm, it feels warm because there's heat flowing out of it and into you. The heat is flowing from that warm thing into you, which would be a colder thing. Or vice versa, if you touch something cold, it feels cold because it is removing heat out of you, and you have heat flowing out of you and into it. It would be strange to touch something hot and have it feel cold, because that would indicate that heat's flowing from something of lower heat to something of higher heat. And so one of these just nice rules of heat is that it flows from a high heat to a low heat. We can kind of think the same thing of water. We know that water flows from a high area to a low area. We know balls roll from high heights down to low heights if it's on a hill. It all has to do with energy, going from a higher energy to a lower energy until things level out. So there I mentioned sort of like water flowing from a higher area to a lower area. Heat will level itself out just like water would if you had two pails connected with a tube, and one pail had very little water and one had a lot of water. They're going to fill each other up until they have the exact same height. And heat does the exact same thing. If you have two objects in contact with each other at different temperatures, the heat will move from the higher heat to the lower heat until they are at the exact same temperature, and then they've reached a thermal equilibrium. So we know that heat flows spontaneously from hot to cold. That's really what we're saying here. Now that word spontaneously or spontaneous is one of these words that has a very different meaning in chemistry than we have sometimes in our everyday life. A lot of times when you think of something being spontaneous, you think of something happening immediately, like right now. And that's not the way spontaneous works in the world of thermodynamics, chemistry, and physics. What spontaneous means is that it happens without a continuous application of energy. So balls roll downhill. That is a spontaneous process. Something exploding, that is also a spontaneous process. A piece of iron rusting in the open air in a humid environment, that is also spontaneous. It's really slow, but it's spontaneous. You don't have to continuously add energy for it to happen. So anytime we're thinking about something being spontaneous, it just means that it occurs without having to constantly apply energy. It's going to be an important term as we go through this set of lectures. Now, just because something is spontaneous does not mean that it can't go the other direction. We can force reactions to go in a non-spontaneous direction, in the same way that we can roll a ball up a hill. We know that we can roll a ball up a hill because I'm sure you've done it many times when you were a child. And what do we have to do to make something move in a non-spontaneous direction? We have to apply energy. If it's moving in a non-spontaneous direction, then you have to have a constant application of energy. As soon as you remove that applied energy, then the process stops going in the non-spontaneous direction. So another example of that is refrigerator and air conditioning. How those devices work is to actually compress gas back into a liquid in the compressor to remove that heat. And we need energy in order to do that, which is why your refrigerator and your airco has to be plugged in. It can't just do that all by itself. So work has to be done on the system. Now, one of the things we want to talk about when we're looking at gaining or losing heat is the idea of heat capacity. Now, we know that when a system absorbs or loses heat, its temperature is going to change. However, the amount of temperature change is dependent on the material itself. How do we measure the amount of heat? You might say, well, it's based on the change in temperature. But it's not, because we can apply the exact same amount of heat energy to two different materials and we would see a different temperature change, even though the amount of heat is the same. So we have to be careful because heat and temperature are very different things. Heat is an amount of energy, whereas a temperature is a measurement of kinetic energy. So they're different. They're different things. So one of the things that we use to connect those two temperatures, the amount of heat and temperature, is this idea of heat capacity. And heat capacity represents how much heat is required to change an object's temperature. Now that seems like a strange thing to think about, but let me give you an example of heat capacity that you know inside your head without really knowing what heat capacity is, perhaps. Imagine that you're sitting around a campfire and somebody asks if you want to roast some marshmallows. Hopefully you know what those are. So would you want to put your marshmallows on a stick and hold it in the fire, or would you like to put your marshmallow on a piece of metal and put it in the fire? Hopefully you said the stick. And the reason you know that is because that stick is not going to get hot, whereas the metal would get hot very easily. And that's because your metal has a very low heat capacity, which means it changes temperature very easily. On the other hand, wood does not change temperature very easily. It has a very high heat capacity. So you can put a stick in the fire for a long time and that stick is not going to get hot because that heat is not going to be conducted. It's not going to change the temperature of that stick very easily. So we can express heat capacity in a couple of different ways. We can express it as molar heat capacity. This is the amount of heat needed to raise 1 mole of a substance 1 degree Celsius. We don't actually use molar heat capacity very often because we're not always dealing with moles of a material. You might see it in specific disciplines, but generally what we use is something that is called a specific heat capacity. And so we use the letter C, a capital C there, for specific heat capacity. And that is the amount of heat energy needed to raise 1 gram of a substance 1 degree Celsius. So I just have 1 gram of a substance and I want to raise its temperature by 1 degree Celsius. Now the interesting thing here is that it doesn't matter what the temperature is. It takes the exact same amount of heat energy to raise it from 2 Celsius to 3 Celsius as it does to go from 85 Celsius to 86 Celsius. It's exactly the same. So heat capacity is not dependent on the temperature of the material. So both of these quantities are intensive properties, which is nice. We do enjoy intensive properties. Intensive properties, if you remember, are those properties that are independent of the amount of material. So it doesn't matter if I have a kilogram of material, I can look up its specific heat, or if I have a gram of material, I can look up its specific heat. And the reason they're intensive properties is because they reference the amount of heat for a very specific amount, just 1 gram or 1 mole. And so that will never change. If you have more than 1 gram or more than 1 mole or less, then you just adjust the amount of heat needed for the amount of material that you have. And we'll see an equation to do that here in just a little bit. We use that specific heat capacity most often, as I mentioned. We don't use molar heat capacity very often. So again, we use that specific heat capacity to quantify, okay, and that means assign a number to the amount of heat transferred based on the mass of the material and the temperature change either observed or that we want to see. So we have a nice equation here where we have heat in joules is equal to Q, okay, where Q is the amount of heat. Remember, Q is always heat. Okay, so we've got Q there. So heat is equal to our mass of our material in grams times the specific heat. Sometimes you'll see a little S down there that just means specific, means it's being done per gram. If you wanted the molar heat capacity, you might see CM. Usually you'll see just C, and that will usually mean specific heat capacity because that's the more common measurement to use. So if you ever see me just write C, which I usually do, I'm talking about the specific heat capacity using the gram material. So we do have some weird units for the specific heat capacity. It's joules per gram per degree C. One thing I think that the authors should do here is to put parentheses around those two because they are both in the denominator. So joules per gram degree C. And then we take that specific heat and we multiply it by our temperature change. So MC delta T represents heat and its relationship between mass, the specific heat capacity of the material, and the temperature change observed. So let's see an example of how we use that. So let's say we have 15 grams of liquid water. We are going to do something to it. We are to raise its temperature. We're going to raise its temperature from 20 degrees Celsius to 50 degrees Celsius. Now, specific heat of water is 4.184 joules per gram degree C. I apologize, the units didn't show up there. I changed my slides and the units were in black on a white background. When I changed the background to black, the units didn't show up. So they're actually there somewhere. They're just in black, so they're not showing up. So we see them there down in the equation, joules per gram degree C. So do we have an equation that relates grams, a change in temperature, and specific heat capacity? The answer is yes, we do, because we just saw it. We have Q is equal to C times M times delta T. We're looking for Q, the heat, so we can just apply everything else. So we have our value for C, our 4.184 joules per gram degree C. We have our mass, 15 grams, and we have our delta T. So very important here, we have delta T, 30 degrees Celsius. That's the difference of between 20 and 50. Now, anytime you're looking for a delta T, any delta really, you want delta T is equal to T final minus T initial. So here it would be 50 minus 20, which is 30. Now, what if we were going the other direction? What if we were removing heat? What if the temperature was dropping? We would still use temperature final minus temperature initial, and that would indicate that we would have a negative delta T, and we would get a negative value for the heat. Again, remember that negative values for heat or positive values for heat only indicates, I shouldn't say only, always indicates two things. The positive or negative indicates heat flow, and the value indicates how much heat flowed in that direction. So here we see that we have a positive heat flow, and that means that heat went into the system. And we see it went into the system because the temperature got warmer. So we know that heat went into that water. If it got colder, we would have seen a negative heat. Like if we went from 50 to 20, we would have calculated the exact same amount of heat, but the value here would have been negative because the change in temperature would have been negative. And that would have indicated that energy went out of the system and it got colder. Hopefully that makes sense. So here's an example for you to try using copper. So we see that this copper absorbed 43.6 kilojoules of heat. You really want to keep in mind that that's kilojoules of heat. And the temperature rose in the copper by 75 degrees Celsius. Now here you need to determine the mass of the copper in kilograms, and we're given the specific heat capacity of copper at 0.385. Notice how much lower that specific heat capacity of copper is than water. Water was 4.1, copper is 0.38. It is 10 times harder to raise the temperature of water than it is to copper. Okay. Water is actually very difficult to change the temperature of. If you've ever tried to melt ice with a blowtorch, you've probably seen that firsthand. So you'll see a solution to that one on YouTube, so keep an eye out for that one. Now we can also have heat transfer. We talked about this a little bit ago. We talked about how if you have two objects together and they're of different temperatures, you're going to have heat flow from the higher energy to the lower energy. So you're always going to have that exchange of energy taking place if they have different temperatures. So I want you to imagine taking a warm block of metal, placing it into cold water. So if you do that, the metal is going to be really warm. It's going to lose heat to the water, and so the water is going to warm up a little bit. The metal is going to cool down until the metal and the water are exactly the same temperature. Now, heat is a quantity that does have to be conserved, and so the heat gained by the water has to be equal to the heat lost by the metal. The temperature change does not have to be the same, but the quantity of heat exchanged does have to be the same. So we can relate this whole thing into the system and the surroundings. We just need to figure out what we want to use as the system and the surroundings. So if we relate the amount of heat exchanged here, we know that the Q of the system, so the amount of heat gained by a system, is going to be equal to the opposite of the heat gained by the surroundings, or the change in energy is going to be different from the surroundings. They're going to have opposite signs, same value. That's probably the best way to say it. So the amount of heat exchange is going to be the same. They're just going to be flowing in opposite directions. So let's make the metal our system. Let's make the water the surroundings. Okay, so we saw that Q is equal to mc delta T. So we can say that the Q of the metal is equal to the mass of the metal times the specific heat of the metal times the change in temperature of the metal. And that has to be equal to the heat gained or lost. I guess it would be gained by the water. So that would be the mass of the water times the specific heat of the water times the temperature change of the water. Okay, so both of those things are equal to the heats lost and gained by both of those entities. So here's one for you to try. We're going to take a block of copper of unknown mass. It has an initial temperature of 65.4 degrees Celsius. We're going to put it into a beaker of water that has 95.7 grams of water in it. The water is initially at 22.7 degrees Celsius. The two substances reach thermal equilibrium at 24.2 Celsius. So what this means is that they have different starting temperatures, but they have the exact same finishing temperature. So your delta T's for the two materials are going to be different. Okay, so we want to know, what is the mass of the copper? We have the specific heat of the copper here at 0.385. The specific heat of water you can find in a couple slides back, and you will see this example worked out on YouTube. So look for that link. So let's talk a lot about our heat exchange. Let's talk about work. Pressure and volume is probably the most common way that we do work in chemistry. We know that pressure is a force that acts against the sides of a container. And if you remember from your physics, work is force times distance. So pressure is a force, and so we just have to move something. So if we have that pressure moving something like the walls of a container or a piston, then work can be done. There we go. So work can be expressed as the negative of the pressure times the change in volume. The negative that we put there is just so that work has the appropriate sign as far as work being done by the system or being done on the system. So we have pressure times the change in volume. So you can imagine we have a certain pressure, and if it's expanding a volume or decreasing a volume. So if we're going to do work on the surroundings, then we can have that like a sample of gas expanding against the external pressure, causing a vessel to expand, something as simple as a balloon again, or something like a piston. So let's look at an example here using a balloon. We want to know how much work in joules, and work has a joule unit just like energy. So we want to know how much work do we need to do in order to inflate a balloon that's 0.1 liters, so that would be an empty balloon, and we want to inflate it up to 1.85 liters, and we're going to do that against atmospheric pressure. Now I apologize for my use of atmospheres for a pressure unit. I know a lot of you have not seen that. You can use liter atmospheres. Some of you have used pascals or kilopascals. I've always used atmospheres. It's just more common, or I've done my chemistry in the past. I have looked at using liter atmospheres as well. So I've got that in here too. So we have work is equal to negative P delta V. Now our delta V is going to go from 0.1 liters to 1.85 liters. So again, we always use final minus initial. So my final volume was 1.85 liters, my initial volume was 0.1 liters, and so my delta V is 1.75 liters. Our external atmospheric pressure is 1 atmosphere, or 1.75 liter atmospheres. Okay, and 1.75 liter atmospheres is also equal to 101.3 joules. So we can take our 1.75 liter atmospheres, that's my pressure times my change in volume, I get 1.75. Convert that into joules, which is 101.3 joules per liter atmosphere, and we end up with negative 177 joules. So once again, let me go through that because I'm not sure I explained it very well. We've got our work is equal to negative P delta V. We have our P right here, 1 atmosphere. We have our delta V right here, 1.75 liters. Our work is equal to negative P delta V, so we have negative 1 atmosphere, that's our P, times our delta V, 1.75 liters. And so the work done is negative 1.75 liter atmospheres. So what that means is that it did work on the atmosphere, and it moved the atmosphere out of the way, so the balloon did work here. Now, if we want to convert liter atmospheres into joules, we have this conversion right here. 1 liter atmosphere is equal to 101.3 joules. And so now we just do that conversion right down here, and we get negative 177 joules. So 177 joules of work was done, and it was done on the atmosphere by the balloon. The balloon was the system. All right, well, that finishes out our discussion of heat and work. Hopefully it made some sense to you. If not, please contact me with questions.